Let's try to find the volume of a sphere that has a radius that's unknown, but we'll just call it r. And now we already know that there's an equation for this. We can look it up in the Google or on the textbook, but it's kind of interesting to think about how this might have come to be way back 300 years BC when they were first trying to figure out what the size was of spheres, and they actually were using cylinders to help them with that approximation. So we're going to write with some algebra here and identify what the function is that represents the curve that we're about to rotate. And so I've chosen square root of r squared minus x squared, which you can get from just rearranging the terms that are in the standard form of a circle. And I'm choosing just the positive square root part because we need to make sure that we're still creating just one function. We can't use a bottom layer because we're talking about being rotated around, and we don't want to talk about rotating a bottom function as well. We'll accidentally get a double count. So here you can see that we're just kind of rotating again that around, and we've got a range, or excuse me, a domain that we're considering. That negative r on the x-axis is going to be where the circle touches down, and then we've got a positive r, which is going to be on the right-hand side. So now we should have just about all the information we need to begin to fill all of this into our disk method equation. Recall again that it's going to be the integral from a to b of pi times r squared, but instead of r, our radius here that's being rotated around is really that function. So this is where it's being very careful to make sure our notation is correct. We're rotating around that function, so it's going to be f of x squared, and then those tiny little cylinder heights are going to be little dx values. So now we've got pi times the square root of r squared minus x squared, quantity squared, make sure that you're paying attention to that squared that happens to the function as a whole, times dx. Now from here we can simplify this up a little bit. That square and the square root are going to cancel out really nicely. Now again, this is going to be a point where I stress that knowing what you're writing and why you're writing it is going to be a really important detail here in Calc 2, because these r's that we have for these bounds are known values. Remember that they're going to be something that we are handed at the beginning of the problem. So those are constants. Pi is also a constant. X is the only thing that's changing here because we want to talk about cylinders that could be at any point along that x-axis. Well, if we have pi times r squared and both of those are just constants, then that's a number, and the integral of a number follows the reverse power rule, and we'll just tack on an x and call it good. That latter part, though, is going to be a little bit more. We're going to use the reverse power rule on the x there, and that's going to climb from an x squared to an x cubed, and we compensate with that 1/3, right? That antiderivative via the fundamental theorem of calculus. Now from here we get to just simply evaluate, which is nice. These are numbered bounds that we have. We're only able to have those numbered bounds there, and it's just some given r. And I'm going to choose to simplify my calculations on the first parenthesis by just pulling out the pi and the r squared, because again, they are constants. Keep track of the parentheses when you're talking about minus the evaluation at the lower bound, because you want to use a negative r here and a subtraction. You want to make sure that those are both differentiated. Same thing's going to happen for the latter part. I'm going to choose to include parentheses here as well around the negative r cubed, even though in this case I could skip a step and just recognize that a negative r cubed is going to be negative r cubed. From here we just simplify everything and you can start to see the equation that we were expecting emerge from the work that we're doing. We've got 2 pi r cubed, we've got the pi and the r cubed which we know from the sphere's volume formula, and we've got a couple of fractions, looks like 1's over a third. Let's get some common denominators, simplify this up properly, and you can see that it's going to be pretty apparent that the volume of the cube is going to be calculated by 4/3 pi r cubed.